Okay, let me see.
Recording in progress.
Can you see that? Or can you see my screen? Okay, can I start now or just wait for? Okay. All right. So good evening, everyone. Again, thank you so much for joining this course. So today, I'm going to talk about subsurface investigation method for infrastructure project and what are the different laboratory tests or in situ tests generally done. So, I mean, this is most important thing for any civil engineering project because we don't know what is below the ground, right? So we need to take out the soil sample and then characterize it. Mostly you bring the soil sample to the lab and characterize it. Sometimes you have to go to the site and do the in situ test. So today's lecture basically, I mean everyone knows, but I'm just going to refresh that what are the different subsurface investigations available and what are the different properties you need to measure from the deduced samples. So what is subsurface investigation? So you see the proper civil engineering required adequate knowledge of subsurface conditions at the site of structures, so where the actual construction is going to be. So you need to go to the site and take out. So when you collect soil sample, you need to do the physical properties, and also you need to do the arrangement of deposit underlying material. So basically, you need to make a borehole, take out the soil sample, and characterize it, and then you need to know what are the different depth, what type of soil is there. Okay. So the field and laboratory investigation required to obtain this essential information. So basically, we need to, and then it's called the site investigation. Sometimes it's called subsurface exploration. Sometimes it's called soil exploration or exploratory program. So there are different names. So basically, it's a subsurface exploration. Right. And so it's maybe physical weathering, chemical weathering, physical and chemical weathering process, and then what are the different, transporting. So there may be transported soil and residual soils, and these are forms of millions of years. So we really don't know what type of soil below the ground. So when you construct any structures on any soil, we need to know what type of soil there. Okay, so that's the thing you need to understand. So basically, objective of this is site investigation to determine the location of thickness of the soil strata. So we need to know how much is the thickness of the soil. So it may not be, so the soil, the current location, so maybe 50 meters away or maybe 150 or 100 meter is totally different soil. And the soil layer is formed like a homogeneous, it may not be homogeneous. So it's maybe one layer, maybe thickness is more on the other side. So we never know what is there. Determine the location of the groundwater table. That is very important because the groundwater table fluctuates the soil properties. Again, all these dry unit weight unit weight, bulk unit, all these things are going to change, saturated unit weights, and everything is correlated. Recovery of the soil sample for the laboratory test. So when you take out the soil sample, how much is the recovery? So that is also important. So we'll be talking about whether the sample is representative or non-representative sample, and conduct various laboratory and field testing, and then also identify special problems occurs. Then preparation of a borehole. So boreholes is basically, you take out the soil sample. So you need to know for a particular site, depending on the type of the project. So how many borehole you need to, you need to make, and then also at what depth, what should the spacing, all these things you need to know, and then put it in a chart for any particular borehole. So all the different properties so that geotechnical engineer can see at one time, okay, these are the properties and what to do. So this is what you can say, this is like a blood test report, you can say. So name and so what are the, the bore log should have all this name and address of the drilling company with the driller's name, job description number, number and type of location of boring, date of boring, and then what type of sample taken. So whether it is auger boring, whether it's split spoon sampler, or thin walled selvy tube sample. So most of the time you need to write that. And then also where is the location of the water tables, that is also need to be mentioned. And if it is a rock sample, obviously what type of core barrel has been used, and also the actual depth of coring, and then length of core recovery. And also you need to find out from there how much is the rock quality. Rock quality designation. From rock quality designation, you can find out how much is the quality of the rock. So this is the just sample of bore log. So here you can see the project name, location, boring number, number of type of boring. So everything is mentioned. And over here on the left side, you see the description of the soil. So with the depth, how much, what are the different type of soil is there. And also the third column, you see the standard penetration number. So we have SPT value as N. So that should be corrected. Sometimes while taking this bore log, while incorporating the data in the bore log. So most of the time we use that the raw that SPT number. So then we need to do the corrections. So I'm going to explain that, how to do the corrections. And then also we need to measure the moisture content or water content. And then also you need to write, okay, SS, what is the sample? So basically the split spoon sampler. Sample has been taken, ST is the selvy tube, at what depth, and then also what are the different properties you determine. So this is same thing again, so N value, sometimes you can see over here the depth. So first one is the depth, description, legend, so different type of soil, and then also the sample is here, fifth column. You see the samples, whether it is D is for disturbed sample, whether it is U is for undisturbed sample. So that also need to be mentioned. Okay. And then also, as I mentioned, the earlier ones, the SPT N value. So N value is more, obviously, the soil is strong, right? And then also unconfined compressive strength also should be mentioned sometimes. It depends on what type of project. And then depending on that, people make a borehole and then log this data. So most of the time, people use SPT value. And then for any geotechnical engineering design, we need to know how much is the cohesion or angle of internal friction of the material, okay, for any design. So now the thing is, you have only this borehole and SPT data, nothing else. So most of the time we need to, there are several correlations that are available from SPTN value, how to find out that different friction angle or the cohesion. And then from there you can design your foundation or any infrastructures. So basically, there are a lot of correlations that are available you can use to determine the shear strength parameter. So ultimately, we need to know how much is the shear strength, correct? And for any infrastructure design or foundation design. And then also, obviously, if you want to know that the consolidation stuff, how much is going to settle, so obviously you need to know that the shelby tube sample, and then you need to use the consolidation test. So most of the project, depending on the type of project, so you need to do different tests. Obviously, people most of the time they use this okay, in a particular site, if there is a borehole data is already available in the existing building nearby, they use that as a preliminary guess. But if you want to do actual, the properties of that particular site, so you need to do this borehole. So again, the same thing over here. The project, so site exploration general strategy is the project assessment, literature search. So that's when you have an idea. Field reconnaissance, subsurface drilling and sampling, laboratory testing of the soil sample. So all these things, what are the testing to do in the lab? Project assessment, here, a few things you need to know, the type and location of the approximate dimension of the project development. So again, it's a small project, and the area, so you need to know how many boreholes you need to do. So that one also you need to check. Existing topography of any proposed grading, so we need to check also. And also any previous development. So previous development, if their existing site is already developed, so then you have an idea from the existing project. Then literature first you need to, for any if you unknown site, so we need to know the geology, obviously, what type of, how the soil is formed. Again, this rock cycle, you need to know that igneous sedimentary metamorphic rock and how the different weathering process, all the different soil forms. So we need to know that. And then the soil survey report, geotechnical report, and historic groundwater table data. So also we need to know what are the fluctuation of the water table and the location of the groundwater table. Because this water table really, is very important because the properties of so dry you need to wait, to saturated you need to wait, or submerged you need to wait. So properties of the soil is going to change, with water. Then these days, a lot of remote sensing data, there are these days, a lot of GPS, other things, people are using to calculate or to gather all this data. USGS also have their own data, available, but not too much detail. But you have an idea what type of soil is there in a particular area. So conventional aerial photographs people take, and also infrared aerial photographs. And then from there, depending on the vegetation and other things, people already correlated, okay, this type of plants or this type of vegetation, what type of soil is there in the particular site. So this will give you a little bit of idea. Field reconnaissance, obviously, any previous development or grading, etc., site topology, or any sign of slope stability, instability. Site drainage condition is also important. Also, the rock outcrops and site access. Field exploration, as I mentioned, so you need to go to the site and take out the soil sample on a particular site. So site boring layout, so you need to decide as a geotechnical engineer, so depending on the site, how many boreholes you need to make, what should be the depth, and a test boring or test pit, it depends on the type of material, what you want to know. Number of and frequency of the boring, that is also very important. And then how much is the depth, sampling method, and then also field testing. So this is field exploration. So this is the particular area. And then you see that the different, the dark circle, this is the boring hole location. So these are the different borehole locations. So most of the time we do the, the borehole where the actual foundation is coming, so that we have more control and we know what type of soil is there. So then you can design your foundation or any infrastructures effectively. Because if there is a thick layer of clay, we need to know how much is the length, depth of the clay, at what depth. So then you can calculate how much the building is going to settle. So all this information you need to know. So boring space, again, the site conditions and uniformity. So if the soil is, most of the time, the soil is not a homogeneous material, correct? So, different type of soils. And at the site, you'll not get the pure, like a coarse grain soil or fine grain soil or cohesive soil or maybe cohesionless soil. It is a mixture of different soils. And as I mentioned, it can be silt, sand, gravel, and clay. It can be mixed with all this different material. So, and then also type of structures, what type of structures you're going to make. So again, depending on the structures, you need to be careful. And then also typically one borehole part, 2,000. So this is just like approximate guideline. You need to make 2,500 feet square part one borehole. And depth of borehole, that depends on the magnitude of the loading and the soil conditions. So these are some guideline again. So as you have seen, if the soil is very poor or erratic, because the soil properties are varies, then you need to do the lesser area. You need to do more boreholes, right? So if you have a soil is very high quality or uniform soils, similar type of soils, so then you can increase the area and the number of boreholes. Okay. So you see here one borehole every 50 to 100 meter of site for compressible soil of limited area. Then one borehole for every 200 to 300 meter, compressible zones of various ground surface. And then one borehole every 500 meter on the site of homogeneous ground. So the soil is homogeneous, uniform, so no need to do more boreholes. So then the spacing, approximate spacing of the boreholes. What should be the spacing between one borehole to another? So depending on the project, so you need to use different borehole, the spacing. So if you see the multi-story building, so again, these are the guidelines. Multi-story building, so 10 to 30 meters. So is a dam and dikes, obviously is 40 to 80. Residential subdivisions, so highways is 200 to 500 meter. So these are the spacing of individual boreholes. And then how deep, also it depends on the surface conditions. And so again, if it is a poor, these are the equations. So second column is in meters, the same thing, and then third column is in feet. So if you know how many number of story you're going to construct a particular soil, and D is the anticipated depth of foundation. So basically, at what depth you are going to place your foundations. So you can easily calculate that how deep the boring should go. Obviously, most of the cases, if you are constructing a dam or if you're constructing a pile foundation or drill shaft or drill pier or any sensitive structures, obviously that you should go up to the rock. Okay? Sometimes not even resting on rock, foundation. So it can be even socketed. Even you need to cut the rock and just inside the rock itself, some portion. So the soil borings, obviously you need to take out the soil sample and then the trial pit, and then you need to make a hole using a drilling rig. So there are different types of drilling rigs that are available, and you can take out the soil sample from the ground. So then it's the boring or drilling or sampling, and then so what are the things? Subsurface drilling. So obviously it is below the ground, that's why it's subsurface. So it's auger drilling. There are different types of auger drilling: solid stem auger, hollow stem auger, post-hole auger, helical auger, continuous flight screw augers. There are so many different types of augers. There are wash drilling also. People still use this wash drilling. There are rotary drilling, and there are percussion drilling, and there's Odex drilling. So again, depending on whether we're drilling only the soil or it is going through the rock. So again, if it's a rock, so then you have to use different cutting bit so that it can cut the rock. So this is a boring tool. Again, everyone knows, like a post-hole auger, helical auger, it used to insert it into the soil. So just hand auger also. And then also obviously the power drill. So you need to using a machine so that it can bore, it can make a hole and collect the soil sample. So depending on the situation, so whether you're going to collect the soil sample. So most of the time people use, like I say, clay type of soil, use like a very soft push, not the hammer. So, just Shelby tube sample. If it is SPD sample, it's a coarse grain soil, or clay mixed with, granular soil. So what you need to do, you make a hammer, using a hammer, and then, the sample will be collected using a core catcher and the switch pulls. And then you collect that sample later on. So these are auger drilling. So there are different, I will just show quickly different types of auger drillings are available. The hollow stem auger, how you can see here, there is the casing of the outer spiral, inner spiral rod, and also for removing pilot assembly for the inserted sample. And then maximum depth, it can go 50 to 100 feet. Okay, so this is how we collect the auger drilling. Then hollow stem auger, again, So that can get SPT test sample test results. Cannot penetrate very strong soil or rock, and then also it problem when the samples below the groundwater table. So groundwater table is there, so then you cannot use this. Is a problem. So there are different types of hollow stream auger. How it looks like, I already mentioned. So this is drilling with flight auger. Sometimes, most of the time, you just make a for any, just for example, pile foundations. Okay. So when the soil is good, you need to make a hole into the ground and then just take out the soil sample and shake it. The soil will go. If the soil can stand at its own, so without casing is required. So if the sample is going to collapse, so then you have to have that the casing. So this is again the washboarding. So we use some water jet to make a hole into the ground, and then drilling rod and chopping bit, and there is a casing also there, and then you can collect the soil sample. Rotary mud or air drilling. So these are the different types of drilling. So basically, you can use rotary drilling, the bit at the end, the drill rod to rotate and advance. It can be used for soil and rock cutting by circulating drilling fluid. And also the common bentonite is and water slurry of density. So sometimes, when use that making a borehole, sometimes the sandy type soil is try to collapse. So in that situation, use that the bentonite slurry so that the soil can be stabilized. Okay? The cable tool drilling. So there are different types of, I'm not going to go in details. So rock drilling, coring or augering. So again, there are different types of attachment you need to add. So cut the rock, and then also depending on how much is the recovery of the rock, so you can calculate by using this the rock quality designations. Okay. The sample. Now the sample is so now you have seen that different types of auger and boring tools. You just collect the soil sample from the ground. Okay. The soil is collected from the borehole for testing, so it's known as soil sample. Now the thing is whether the soil is representative or non-representative samples. So the method of often the soil sample is termed the sampling technique or simply sampling. The tool which used to collect the soil sample is the soil sampler. Okay, that is a sampler, and depending on the presence of soil constituted in the sampled soil compared to the in situ, the sample may be classified as representative or non-representative. So the thing is, when you collect soil sample, whatever sample collects, whether it is representative or not. Okay, so representative sample is the one which there is no changes in the soil constituent. Sometimes the soils at different depths while hammering or anything SPT samples, the samples are mixed. Okay, so and then also while doing that, take out the soil sample. The structures of this soil sample is getting changed, or water content is getting changed, void ratio is getting changed. So if everything is maintained, then it's called a representative sample. Non-representative samples, if the soils are mixed or some of the soil constituent of the samples are missing. So sometimes when collecting the soil sample, if there is a water table in the sampler, soil sampler, the sample can fall. So in that case, that is not representative of the particular depth, okay? The soil sample collected. So that is non-representative sample. So again, rock and soil sampling is the disturbed samples and then undisturbed sample. Okay. So disturbed sample is in place, structure is not preserved. So, but still you can do soil index properties like a liquid limit test, plastic limit test, particle size division test, all these things, the different physical properties test you can do. Okay. But for undisturbed sample, we need it, minimizes the effect of potential disturbance. So we need to do in situ density, okay, or in situ permeability, or soil shear strain, or the compressibility. Sometimes we need to do that for the undisturbed, undisturbed sample. We need to have undisturbed sample because you see, as I mentioned in the last class, like when it's a clay type of soil, clay has different fabric arrangement. So it can be floccular, it can be dispersed. So depending on that, although you can maintain the same density, in the lab, but you cannot really replicate the fabric. So that's why most of the time, the disturbed sample, the fabric arrangement is disturbed, and we need to do the undisturbed sample most of the time to measure this permeability, just for example, and then go to the site and do the permeability test for better representation of the permeability value. The soil sampler. So there are different type of samplers you can use to collect the soil sample. One is the SPT or split spoon sampler, SP, split spoon, and one is Selby tube samplers. So you can collect the clay type of sample, piston samplers, and then heavy wall samplers. So there are different type of sampler. So standard split spoon sampler. So basically, it's a thick wall sampler, and it can divide into two half. And then also, while doing this, you need to hammer it into the ground. Okay. So over here, you see the diagram of the standard split spoon sampler. And then also when you do unassembled, it looks like this. Okay. So these are standard sizes. Everything is there. There is a cutting shoe, and then we hammer it, So now the thing is, obviously, if you want to collect the undisturbed sample, so you need the thickness of the sampler should be very thin. Okay. And then also there should be cutting edge. And obviously, the design features governing that degree of disturbance, the cutting edge, inside wall friction is also important. And the non-return valve also we need to check. Okay. So how do you know the sample is really disturbed or not disturbed? Okay. So when you collect the soil sample, depending on the sampler is basically a tube, as I mentioned, correct? So we need to know the diameter of the tube. We need to know the thickness of the tube, right? So for Shelby tube samples, the thickness is very less, so that you can push the sampler into the clay, and the disturbance will be minimum. So if you have a thick wall, and obviously when we hammer it, the sample is getting disturbed, right? So what you need to do, you need to calculate the area ratio, and you need to calculate the inside clearance and outside clearance. So if you know that the outside diameter of the sampling tube, if you know the inside diameter of the sample tube, then you can find out the area ratio. And if the area ratio is less than 10%, so meaning it's a good quality sample. Okay. So these, and then the area ratio represents the volume of the soil displaced by the sampler as a ratio of the sample volume. And then the larger the volume of the ratio, the larger the sample disturbance. And most of the time, if the area ratio is 10, it's a very good sample. And sometimes area ratio up to 25% even considered to be good. So depending on the situation. So this is Selby tube sample. So this is a thin wall sample. So when you collect mostly the clay type of soil, just push it to the ground. And then you see there is a hole on the top of this, the Shelby tube. So most of the time, the bottom is the cutting shoe, it's this thinner one. And then when the Selby tube is done, when you are pushing to the ground, and you just make just take it outside using this hole over here. Okay? And then obviously when you collect the soil sample, you need to put it in a vertical, put it in vertical, like as you collected the soil sample, in vertical directions, and then bring it to the lab. Okay. Piston sample, again, you see there's a piston over here in the Selby tube sample. So that will be just like the syringe, it can hold the sample, So minimize the sample disturbance caused by the back pressure. So apply some back pressure so it can hold the soil sample. Heavy walls, obviously, sample will be disturbed. Okay. Then also, this is important, the groundwater monitoring. So obviously, you need to use the standpipe using piezometer. And then there is a different type of sensor. So make a borehole and then put a sensor into the ground, into the borehole. And when it touches the water, it will give you immediately how much is the water groundwater level. So most of the time, you need to make a borehole depending on the site. If there is a clay type of soil, it is not that water will come to the borehole immediately. So we need to keep it for 24 hours and then measure the water when the water level is steady, meaning that all the surrounding water already came into the borehole. So again, there are different perforated pipes, and sometimes we need to use that steel pipe with the grit, and then also sometimes you use the geotextiles also. So this is thin wall tube sampler, how it looks like. So as I mentioned, so we need to know how much is the outside diameter, how much is the inside diameter, and that is a cutting shoe. So we just push it to the ground, okay, to correct the thin wall tube sampler. So these are again what is the mechanism, the piston samplers, to collect the soil sample, and we're going to go in detail. Here, the rock coring sample, again, there should be cutting bit and the coring bit, and then also how to collect there should be the single tube core barrel and the double core barrel. And then when you collect the soil sample, using this the drilling or sampling the core, so you need to know how much is the recovery. Okay, sometimes if it is a weathered rock and the fractured rock, so you will not get exact intact rock sample. So depending on how much is the length of the coring, so you may not get exact the same length of the recovered sample. So so what you need to do, you need to take that the recovered sample, which is greater than 4 inches, and you add that all portion is greater than 4 inches. How much is the length divided by the length of the core? Okay, the total length of the core to recover the soil sample, the rock sample. So then you can calculate the rock quality designations value. So basically, you need to add that more than 4 inches sample recovered divided by length of the core. Okay. So then from there, you can find out if the rock quality designations is less than 25%, it's very poor. If it is 25 to 50, it is poor. If it is if it is around 90 to 100%, is an excellent. So meaning if you have a sampling tube of this much length, so you calculate the whole length of the tube, the recovered sample intact. So that is like an excellent intact sample. But sometimes you may not get that because of the fractured rock and weathered rock, depending on, again, what type of rock is there. So it may be sedimentary, it may be igneous, it may be metamorphic, all these, or maybe slate, different types of rock there. So depending on the rock, you will get that different type of RQD values. So now there are different in situ tests. Again, I'm just going to go all these different tests. It's very common, as I mentioned, the SPT or standard penetration test. The value generally denoted by N, capital N, and from N value, you can find out if the N is more, meaning the soil is strong. Then the cone penetration. So we have a standard cone. You just push it into the ground, and you need to know how much is the end bearing, and then how much is the skin friction or tip resistance and the skin friction. Easily you can calculate from there what type of soil, and it is connected to the computer. So easily you can find out. It's very quick. Only disadvantage is cone penetration. You will not get the soil sample, actual sample, but it will give you an idea what type of soil is there below at what depth. Vane shear test, sometimes the soil is very soft. Even when you collect soil sample from the field, the sample is already disturbed. So then what you need to do, you need to go to the site and do the test there. It's called the field vane shear. Sometimes you can do the test in the lab, so the lab vane shear. Pressure meter test, also it is in situ test. You go to the site, use the pressure cell, make a borehole, and then apply pressure. And then what is going to happen, how much is the resistance from the side. The soil is strong, so it will more resistance is going to offer in the lateral direction. So we can find out from there what type of soil. And then also the flat plate dynamometer, so similar type of equipment. you can use that. And then the borehole shear test, also the plate load test. Plate load test, again, you go to the site and then do the test at what level the foundation is going to be, and you just put a plate, standard plate, and then apply load. And then obviously you can find out the load settlement graph from there. And depending on what type of soil, there are different correlations that are available. So if you know how much is the plate size, how much is the settlement of the plate, then you can find out if you know how much is the width of the foundation, or if you know the width of the foundation, then you can find the actual foundation, how much the foundation is going to settle. So all these things you can easily find out from the plate load test, or the field test. The lab, go to the site and do the field test, the plate load test. So these are, as I mentioned, this SPD value, the standard penetration test. There is a standard test, there is a standard hammer, and there is a standard height of fall, and just put it into the ground most of the time. So so you need to calculate the first 6 inches, you ignore the second. So I'm going to go in details. And then the vane shear test. So vane shear test is when the soil is very soft. We have a vane, is basically just like a cross type of stuff. So we just rotate, apply some torque. So you need to, when you know how much torque you have applied. So the shear, it will be forming a cylindrical surface, and then you need to know how much is the resistance, how much torque you applied, you need to know how much is the resistance applied around the periphery of this, the shear. So, and then also at the top and bottom, so you can easily calculate how much is the strength of the soil. Then the pressure meter test, as I mentioned, so we just apply pressure on the lateral direction. So how much is the resistance offered on the side? So easily you can calculate how much is the stiffness of the soil. And there are correlations. The CPT, as I mentioned, is the cone penetration test. So you can just push it into the ground. You can also collect the soil sample using, if you attach a special attachment, most stuff, you can attach it, and then you can collect the soil sample also from there. And then also that the diameter test. Okay. So, and then also the dynamic cone penetration test is also there. So it is people are using this, but there is a standard hammer, and then just fall into the ground. Depending on height of fall is 575 millimeters, depending on the soil type, how much the penetration, there is a relation between that. From there, you can find out the dynamic penetration index. So obviously, and you can easily calculate, you have an idea what type of soil at the site. So these are different boring, as I mentioned earlier. So few things, as I mentioned, when you collect soil sample, we need to check that how much is the recovery ratio. We mentioned that area ratio. We need to know the recovery ratio, the actual length of the recovered sample divided by theoretical length of the recovered sample. So this one for the soil, this is for the soil. Again, LR is equal to 1, indicates the sample is relatively undisturbed. So if LR is more than 1, the sample is expanded or loosened. So that one you have an idea. So again, this is for the soil. For the rock is different. For rock is how much is that more than 4 inches. You can add all this and then divide by total sample length. SPT is, as I'm just going to tell, this is very common thing people use, and most of the borehole people have that, just only the SPD value. SPD is the hammer is 63.5 kg hammer, and the height of fall is 76 centimeter. And so total penetration is 6 inches plus 6 inches and 6 inches into the ground. And we have a standard SPD sampler. So just 6 inches, 6 inches plus 6 inches. The first 6 inches you just ignore. And every 6 inches penetration, you count the number of blows. So that is N value, that is a raw N value. So first 6 inches and the second 6 inches, you calculate how many number of blows, you just add that to, that will be the actual SPD value. Okay. So what is the advantage of this SPD test? Is inexpensive, is availability, sample off-chain, huge database, able to penetrate local hazard. Okay. And then disadvantages: operate independent, accuracy is poor, not good for gravel, so it will be difficult to penetrate. No continuous profile, no good correlations for clay. Again, for clay, you cannot just use that. So because you need to use this Selby-tube sampler. This is how it looks like. Split spoon sampler. So this is so it can divide into two, and then also there is a cutting shoe over here, and then you see there is a core catcher over here. The core catcher that should be attached like over here. You see the my pointer here, so that should be attached there. So most of the time when you push it, this will just open up, okay, and then when the sample is inside, just is closed. So when you lift it up, the sample will not fall. So that is core catcher, and then you can collect the soil sample from there. So these are how it looks like, this the core catcher, and then when it, as I mentioned, it open up and then it can hold the sample. So there are different types of hammer, again depending on the location. So how the hammer is lifted, and just do like this, just whether you lift the hammer manually or just using crane and just drop it, okay? Or using some machine or pneumatic tools and then just lift it up and then do this. So depending on the type, and so that's why there are a lot of corrections is required for SPT N value. So over here, so you see the boring of, so basically at what depth you need to do, okay? So the 50 blows are required for every 150 millimeter or increment. It's 100 blows are often to drive required 300 millimeter or 10 successive blow procedures, no. So when you do like your number of blow is more than 10, and that is sampling, it is not advancing. So then you have to stop, okay? So no need. So then, depending on what type of hammer you are using, what is the efficiency of the hammer, so then we need to do the different corrections, okay? So, so most of the cases we do, if the efficiency of the hammer is 60 to 70%, and do the correction for that. So again, the energy ratio is the actual hammer energy to the sampler divided by input energy times 100. And then also, as I mentioned, so you need to do the correction. So sometimes N60 or N70. So there are different, you see the N70 is CN, that is the adjusted for the effective overburden pressure. And then N is the one actual raw in value. And then mu1, mu2, mu3, and mu4, these are the different correction factor or adjustment factor. And that depends on over here, okay? So this can be for the hammer, different type of hammer has different correction. Depending on the rod length, sometimes you have to attach the rod if you go deeper depth. So most of the time is 1 meter, 1 meter, 1 meter, you attach it. And then the sample corrections you need to do the borehole diameter correction. So all these different thing correction you need to do, and then you get that. And then also depending on the efficiency of the hammer, N60 or N70. So then you will get that, the actual corrected in value, okay? And as I mentioned, so over here, these are the relations with the angle of internal friction with the corrected in value. As I mentioned, we need that C and phi value for any design of foundation or any structures, okay? So the number of correction applied to the recorded number of blows, so as I mentioned, the efficiency of the driving system, what type of hammer you use, length of the driving rod, overburden pressure, this is very common. And then also we need to use the water table, okay? Then the cone penetration. The cone penetration is less robust than SPT, much faster, obviously. And only thing is no sample collection. So this is mostly people use the Dutch cone. The Dutch people, they started. So that's why we sometimes call the Dutch cone. The angle is 60 degrees. Just, there is no hammer, just push it into the ground. And then depending on, you need to measure how much is the tip resistance. So most of the time, the soil is granular type of soil or cohesionless soil or sandy type soil. So then the tip resistance will be more. If the soil is clay, the tip resistance will be less, but there will be friction will be more, and the slip friction will be more. So with the depth, you can find out what type of soil below the ground, okay? So, and then you can find out the friction ratio from there. So you see the QS is how much is the, the tip the skin friction, and then QC is how much is the cone penetration. Okay, so from friction ratio, we can easily find out what type of soil is there at the particular site. And the direct application to the piling, so we can do that. And then also the E is a function of over here, the QC again. So here how it looks like. So again, there are electric cone and there are piezo cones. There are different samples. These days, people are using even for the seismic stuff into that, so that you can get the data for the seismic GS as modulus from there. So over here, again, as I mentioned, this is developed in the Netherlands, further developed. So basically, it's a mechanical cone. There are electric cone and then also piezo cone over there. So this is how it looks like. It is mounted inside the car, and then also the sample. These are the different the length of the tube, and then basically at the bottom of the car, the pipe is going down, and then push it into the ground. Okay, and obviously sometimes to push it into the ground, obviously you need to anchor this car itself, into the ground so that you can push it into the ground. This is how it looks like over here, and the sample is pushing. This is how it looks like the cone. So and then this is a closer view. This is the hole over here that the cone CPT cone is really penetrated into the ground. And then again, it will give you advantages. It's very quick, and it will give you the two things. One is the cone resistance or tip resistance, and then also it will give you friction, slip frictions. That is the instrument is inside that, and you will get the skin friction. So and you can find out the friction ratio, how much is the slip friction divided by how much is the cone resistance. You can easily calculate from there. Okay, and then also it will give directly all these three different values. So sometimes, if you go deeper depth, so the cone, instead of going vertically, it may little bit of tilt, and that may go really totally different directions, and it's not vertical. So, but that the monitor computer screen, it will give you how much is the angle of inclinations. So if it is more than 10 degree, so we need to stop that. Okay, you need to do it again. So if it is more than 10 degrees, so it should be, then it is, it will not be vertical. It will higher depths, and then it will be totally inclined. So and then it will give you automatically the cone penetration and the skin frictions and at what depth. So you have an idea. So most of the time, this is the typical data. So you can find out. So obviously, if you see in a particular site, the penetration resistance is more, meaning that at particular depth, there is a sandy type soil. If you see that at particular depth, the skin friction is more, so obviously that particular depth, the clay is there. Okay, so you have an idea. So obviously you need to read this system carefully. So over here, the same thing over here, you see that how much is the total. So obviously how much is the skin friction, how much is the shear velocity, you can find out from here. And then how much is the pore water pressure also you can find out from this data, So again, most of the time you will get these two, and with the depth, how much is the cone resistance? The cone resistance, how much is the skin friction? So easily you can find out these two data, and you have an idea what type of soil below the ground. It's very quick test, and easily you can determine. So no need to take out the soil sample, and then do analyze it and then find out. So, and then you can find out the friction ratio. There are a lot of correlations that are available, CPT and SPT, and then also there are, if you know the CPT, SPT value, there are different design charts that are available. How much is the bearing capacity of the soil? So easily you can calculate or design your structures. Okay. So as I mentioned, so the cone penetration resistance, you can find out how much is the total force and how much is the area of the cone. And the same way you can find out how much is the side friction. So side friction, how much is the friction, total friction divided by the area. So you can easily find out that how much is the friction. Two things you need to calculate. And then also you can calculate how much is the friction ratio. That one you can calculate how much is the tip and how much is friction, and then also slip friction, how much is the cone resistance, you can calculate also from there. And from the friction ratio, if it is less than 1, usually sand. If it is friction ratio is more than 5 or 6, then it is usually this is clay or peat soil. As I mentioned, there are a lot of relations that are available, the friction ratio and the normalized cone resistance. For for most of the time, the friction ratio is more, as I mentioned, is more ratio, meaning it is more towards clay. And if the cone resistance over here on the y-axis, cone resistance is more, meaning this is a granular type of soil, or you see here on the top, sandy gravel, gravelly sand. So it is more coarse grain type of soil. So you have an idea from this graph. And then from the undisturbed or undrained shear strain, there are correlations that are available, so you can find out from the CPD. And there are, as I mentioned, there are a lot of relations that are available from this. So most of the time, either you do CPD, either you do SPD test, and then ultimate aim is you need to find out how much is the shear strain parameter, that is C and phi value. So that's the reason there are several relationships available. So if you know this, like from the CPD value, the cone resistance, how much is the stresses, so you can find out how much is the angle of internal friction of the material. So there are several relations that are available, so you can find out how much is the undrained shear strength of the clay using this cone resistance. Again, the vertical stress and the cone resistance. So there are different the cone bearing values are available. I'm not going to go in detail. There are CPD of the soils, again, the cone resistance and friction ratio. There are people who have developed the Lunar and Christopherson. They have done a lot of relations. If you want to read more paper, so they have they developed a lot of relations. SPD, there are some relations are there. SPD and CPD also. You can find out, the SPD mostly from if you collect the soil sample, you can find out the particle size division graph. And then also for the cone penetration, no need to collect the soil sample. So basically, you can find out how much is the cone resistance. So there are correlations over here. You can find out SPD versus CPD. And then also, as I mentioned, the more sophisticated instrument, the seismic piezo cone. You can use that to find out, again, the slip friction. And then also advantage is here, you can measure the pore pressure. Okay. And then also the shear of velocity you can find out. Okay. CPD versus SPD. CPD advantages over is basically you can measure the pore pressure, you can measure the dynamic soil sample soil properties. It's more reliable. CPD disadvantages does not keep sample, but you can using most stuff sometimes. Will not work with soil and soil with gravel. If it is gravel, you cannot penetrate the cone, and need to mobilize a special rig. So obviously, sometimes when you need to push it to the ground, no hammer, right? So we need to have a special rig. So first we anchor the whole system, and then push it to the ground. Diameter test, again, this is just pushing it to the ground, and then there is a system. So we just apply some pressure there, and from this, how much is the lateral confinement. Depending on that, you can find out the stiffness of the soil. And then also there are, so we have 1 or 5 minutes, maybe 2-3 minutes. So the last method is, I'm not going to go in detail. There are geophysical methods. So again, so obviously there are indirect methods. This is indirect method you can do, or sometimes, so one is the seismic refraction method, a cross hole. It can be downhole method. Electrical estimating methods, there are a GPR, ground penetrating radar method, or electromagnetic induction method. So most of it is seismic refractions. So what you need to do, basically, we have a geophone, and you have just hammer a particular site, and then you have a special geophone. So obviously, the velocity will transfer, and then you collect every geophone, and you can collect from the data, you can find out how much is the different the depth of the different soil. Okay, so and this one is, it can be single one, it can be multi-channel. So there are different channels are using this seismic refraction method, and from there you can easily find out for the shear velocity there is a relations. And then also shear wave modulus. We are not going to go into detail, but if you want to design, you need to know that the G value, shear wave modulus, and then the shear velocity for the different type of soil. You have this shear wave velocity. So from there, you have an idea what type of soil is there. Okay? So basically, from the shear wave velocity, if you know, and then you can calculate the different depth. So obviously, if the soil is very strong, it can, the wave can propagate quickly, right? So and then spectral analysis of shear waves is the same thing. Again, you use multi-channel analysis for the shear wave. I'm not going to go in detail. Electrical resistivity also you can use to find out what are the different soil layer. And then again, this is the 4 electrode method we used. And then from there, if we have passed the current and the voltage, you can find out the apparent resistivity. And from there, you can find out what type of, the layer 1 and layer 2, you can easily calculate what type of soil is there. Again, for different type of soil, the resistivity of the soil is different. So from there is the standard charts are there. You have an idea what type of soil there. Okay. So I think that's all for this, the sampling or subsurface investigation techniques, various subsurface investigation technique. Okay. All right. So yeah, I know that I just go quickly, so there are so many. So basically, the borehole is most important. So you collect the soil sample using different sampling technique, and then just put it in a bore log with the depth and what type of sample is there, what type of, mostly it is N value is there, what is the location of the water table. That's the main thing. As I mentioned, this is like a blood test report. So if you have more confident of your bore log, then you can design your foundation or any infrastructures more economically. So most of the time in geotechnical engineering, if you don't confidence with your data, use more factor of safety. That's all. Geotechnical engineer generally you use more factor of safety when you have when you don't have much confidence on your geotechnical data. So it may not be economical, but most of the cases, geotechnical structures, we don't want any failure. So I mean, if it fails, then it is a problem, right? So there are methods to rectify these days, but much more expensive. Right. Any questions on this? Again, this is everyone knows this. I'm just just revising all this. So for any geotechnical engineering design, we need to know this. All right.
Sir, I wanted to ask one thing. In the MASW that is mentioned, you have mentioned in your slide that inversion.
Okay.
Sir, can slide details, sir? Actually, I will be using, planning to use in future. So,
okay.
Slide details, sir, if you can highlight a few things.
Okay. So here, I mean, I can send, because with the time things, we have not explained. I just mentioned that all these 4 methods, that's all. I have not explained anything at all, for the indirect methods. So most of the time, for these seismic things, I used several times in US here. So most of the time, so we need to really know the softwares and stuff. So that one, basically there are several channels. You need to make a hole, and also sometimes we need to use the borehole, and then the receiver should be inside the borehole also. So there are different techniques. I can send some material to you, maybe, and then we can explain in much more detail, Okay.
Okay, sir. Thank you.
So this is just, I mentioned just only this, what are the different methods. So most of the cases we use that one geophone and then hammer it, and then just hammer it, and there is several geophones. So it will travel, right? So it will go to the one layer, it can go next layer and then go receiving. So most of the time, how much time and the shear velocity you can easily calculate. And again, if you are using that the seismic one, so we need to you can there are instrument is a little bit different. And then also the most important things is you need to really know how to interpret the data. So So using the
Agreed,
software.
sir. The
Sometimes,
frequency,
yeah.
etc., and time history,
Yes,
and all those
yeah,
things
all
we
these
have
things.
to look into. Agreed, sir.
Absolutely, yeah, absolutely. And also sometimes, there are a lot of noise, and you need
Yes.
to remove that noise. Otherwise, you will think this is a soil, different type of soil. So you need to be careful while analyzing the data.
Yes, sir.
Yeah.
Thank you so much, sir.
Mm-hmm.
Yeah, so my question is, just wanted to know the basic difference between SPT and CPT, and which is more convenient to use at site. Now, apart from the difference in results, which is more convenient and which is most preferable.
Okay. Again, geotechnical engineer, it depends on availability of the equipment. Sometimes, I'm in Southern Illinois, even in Illinois Department of Transportation, although we know that SPT is better, depending on the site, but is more sophisticated, it will give you the result immediately. But people still use the SPT method, it's very common over here. It depends on the availability of the equipment, and obviously, if you want to, the CPT is more sophisticated. I think a lot of DOTs over here in Illinois, in US, people are using CPT value, and then also there are correlations are there. So most of the cases, SPT value is easy. Instrument is cheaper. Just only thing is just hammer it, and then 6 inches, ignore 6 inches, another 6 inches, count how many number of blows, and you will get that, the SPT number. Obviously, you need to do the correction. So depending on what type of instrument, hammer you use, efficiency of the hammer, all the correction you need to do, either 60% efficiency or 70%. So you can do the corrections. Other hand, CPT, just push it to the ground and you will get it automatically. But only thing is you cannot use that for totally gravel type of materials. You cannot penetrate. So it is, that is the disadvantages. And also, although it will give you everything, so it will give you a graph. So if it is a cone penetration, end bearing, so it will give you more value, meaning it's the sand, or more sandy or cohesionless soil. If it is the slip friction is more, so in the screen, computer screen itself, so it will give you automatically. And I used, when I used to work for a Dutch company, so I used to do that CPT every day, every 50-meter grid, and most of the time we fill it with sand for the dredging. And then we used to do everyday CPT, and it's very quick. It will give you automatically how much is the slip frictions. Only thing is you have to attach 1 meter, and when you go deeper, you have to stop because it may, it is not vertical. So the angle of inflation is more than 10. So disadvantage of CPT is you will not get the sample, but again, as I mentioned, there is some attachment. So you just push the cone, and then detach the cone, and then push the tube again, and then you can collect the soil sample. And the only thing is you cannot attach the thermostat there, so that the core catcher there. If there is a sandy type soil, that will fall. If it is a clay, then it is fine. So that is the disadvantages of this CPT value.
Yeah.
Does it make sense?
Yeah.
Again,
yeah. We also prefer SPT at site. Most convenient to use.
Because you get the sample, it is cheaper, but again, depending on the availability of the instrument also,
Yeah, true. Thank you, sir.
All right, thank you. Any other question? Okay, so then whatever, I need to share the screen and that's all. But the next session is, so there are a lot of things. I have to, go quick, So you want like a 5 minutes break now? Yeah, okay. Yeah, okay. So now it is like a 7:40. No, not 7:40. Okay, 7:36. Okay, so I'll join soon. Okay. Okay. All right. Thank you.